Hey there, Mr. Sutton here, bringing you the Pre-Cal Honors Chapter 4 Quiz 2 Review Solutions on exponential and logarithmic equations. When we have a situation like this where we have a log on just one side, we can solve this by putting it in exponential form. So we could write 4 to the third equals the input of 5x, or you can raise the base of 4 to both sides. That will cancel out this log because you have 4 to the log base 4, and those are going to cancel. Either way, you're going to end up with 5x equaling 4 to the third. That's going to be 5x equals 64, so x is going to then be 64 over 5. And just doing a quick double check on all these logarithmic equations, 64 is not going to make anything undefined if you plug it back in, so we're good. In a situation like this where we have logs on both sides, as long as there is only one log on both sides and nothing else, we can basically cancel out the two logs, or you can think about it as raising this base of 4 to both sides of the equation. Either way, logs are going to cancel, and you're going to end up with whatever's inside. So 4x plus 2 and negative x minus 3. Now note that you can only do this if there's a log on both sides. If there's a log on just one side, you can't just cross off the log and call it a day. All right, so let's go ahead and solve this. Moving the x over here, that's going to be 5x equals, if we subtract the 2, negative 5. Dividing by 5, we get x equals negative 1. Now, as always on these log equations, make sure you go back and check to see if your answer makes everything okay inside these logs. If we plug negative 1 in here, that's going to be negative 4 plus 2, which is negative 2. If you try to take the log of negative 2, that's actually going to come out undefined. And over here, this also gives us log of negative 2, which although it's the same values we had on the left side, log of negative 2 is still undefined. Because negative 1 actually makes the original equation undefined, it's an extraneous root, and we have to cross it off. And since there's no other solutions, that means we have no solution to this particular equation. For this problem, we have logs pretty much everywhere. Whenever you have more than one log on one side of an equation, you want to try to merge those together using your log rules. Before we do any of that, though, this 3 out in front of this log base 7 of 2, we can actually move that inside, pop that in as an exponent. So that's going to be log base 7 of 2 to the third. And now we can actually combine our logs on each side. On the left side, we're adding the logs, so that's going to mean multiplying the things inside. We can write log base 7 of 6x on the left side. And on the right side, since you're subtracting the logs, we actually divide whatever's inside. So we have log base 7 of 8 over 2. Now I know what you're thinking. If we had 3 log base 7 of 2 minus 1 log base 7 of 2, yes, we could have actually subtracted these logs at the beginning and had just 2 log base 7 of 2, and then popped the 2 in as an exponent on the other 2. So lots of ways to get to what we ultimately end up with on the right side here. Now since we only have one log on each side, we can cancel out those logs, leaving us with 6x equals, this will be 4 over here. And then dividing by 6, we get x equals 2/3. Just to double check, if you plug that into, there's only one variable here, you're not going to be taking the log of a negative or 0, so this answer is good. On this problem, where we have a log inside of a log, you essentially have to undo the logs one at a time, starting with the outer log. So to undo log base 4, we have to raise 4 to both sides, or put it in exponential form. One way or another, we end up canceling out this log base 4, ending up with just log base 2 of x, because that's what's left over inside. And on the right side, we have 4 to the third, because again, this was base 4 that we were raising to both sides. So that's 64 if we simplify that right side. Now I have to undo the log base 2, so I'll raise 2 to both sides. That gives me x equals 2 to the 64, and I'll need a calculator to see what that comes out to. If I raise 2 to the 64th on my calculator, I end up with about 1.8 times 10 to the 19th, if I round that off. For this problem, we're trying to solve an exponential equation. There are generally 2 ways to do this. One is with logarithms, which is going to be kind of messy on this problem. The other is using something called the common base method, where if you can express everything in terms of a single base, you can do the problem usually much faster than using logs. This one, these are all powers of 9, So I'm going to rewrite all of these as 9 to some power. So this 81, for example, that's really 9 squared. So I'm going to write this as 9 to the second, and then outside of parentheses to the 3n. So this 3n gets preserved as an exponent. Next, 1 over 81, that's really 9 to the negative 2. And then finally over here, 1/9, that's really 9 to the negative 1, with a negative 2n minus 2 exponent outside. Now before I do anything else, I need to simplify my exponents as much as I can. Ultimately, I want to end up with 9 to the something on each side. So I only want a single base on each side with simplified exponents. So on the left side, I can multiply these exponents together, giving me 9 to the 6n times 9 to the negative 2. Over here, I can multiply the negative 1 by this exponent, giving me 9 to the 2n plus 2. And we still have two 9s over on the left side. We're going to combine these now. When I multiply bases together, I add the exponents. So this is really just 9 to the 6n minus 2, or plus negative 2. Now that I have 9 to the something on each side, I can cancel those 9s and just set the exponents equal to each other. So I've got 6n minus 2 equals 2n plus 2. Moving things around here, subtracting the 2n, I've got 4n on the left. Adding the 2 over here, I've got 4 on the right. And dividing by 4, n equals 1. For this exponential equation, I can't use the common base method on here. 9, 5, and 33 are not all easy powers, at least, of a common base. So it's going to have to be logarithms for this one. Before I can use logarithms, I want to get 5 to just a single power on one side. So let's start by moving this 9 over here. That'll be 33 over 9, which I could reduce if I wanted, but why bother? I'm just going to use the calculator anyway. Next, before I take the log, I want to rewrite this as an exponent. So using my fractional exponent form, this can be written as 5 to the x over 8. And now that I have a base to a power on one side, I'm going to go ahead and take the log of both sides. So that's going to give me the pop-out rule on the left side. I can write this as x over 8 log 5 equals log of 33 over 9. And now I just have to isolate x itself here. So I'm going to divide by log of 5 and multiply both sides by 8. X then is going to be 8 times the log of 33 over 9, all of that divided by log of 5. And now I need the calculator. This is kind of a mess to enter on the calculator. To make it easier, I'm going to do alpha y equals and this n over d fraction form. The newer calculators have this. If yours doesn't, you're just going to have to be careful with your parentheses. So I've got 8, and I've got log of, well, I have another fraction, so let me do alpha y equals again. Bring up another fancy fraction form here. 33 over 9, and close that parentheses. Down below now, I've got log of 5. Close that parentheses, press enter. And rounding it to 2 decimals, we've got 6.46. And if you really wanted to, you could plug this back in for the x up here just to make sure that it actually works out. For this problem, we have an investment of $2,100 made at 3% annual interest compounded continuously. We want to know how long it takes to grow to $42,000. So with these real-life exponential problems, you want to start by setting up an equation, and you really want to start by picking the right formula. Since we're compounding continuously, out of all the exponential models we've used, PERT is the best one. So we have f of t equals p times e to the rt. This is only for continuous compounding, as far as we know. It ends up getting used in other places later on, but this is the main use right now. So what do we plug in where? Well, since we're trying to solve for t, because they said how long, we're going to have to substitute for everything here except for t. So this f of t, for example, we need to plug something in for that. That is our target amount. That's what we want our money to grow to, which is this 42,000 piece. P is what we're starting with, our principal. That's 2,100. And then the rate, that's 3%, or 0.03. And E is playing itself in this motion picture. Plugging all that stuff in, we have 42,000 equals 2,100 times e to the 0.03t. And this is just a exponential equation now. So we have to isolate our exponential term, dividing by 2,100. 42,000 divided by that ends up being 20. Now that I've got my exponential piece isolated, I'm going to take the log of both sides. On this particular problem, since I have e, I'm going to take the ln of both sides. We could always take the ln, but it's really useful here because the ln of e is just 1. So using my pop-out rule, I have ln of 20 on the left, and now really using my pop-out rule, I have 0.03t times the ln of e on the right. But ln of e we said was just 1, so I'm not going to bother writing ln of e right here, but it really is there. It's an invisible ln of e. Next, we just have to divide by 0.03 to get t by itself, and we need the calculator now. So ln of 20 divided by 0.03 comes out to, that's a long time to wait, 99.86 years. Well, you might want to get a day job while you're waiting for that money to grow. For this problem, if the half-life of the element air-surlium is 9 months, how long will it take a 40-gram sample to decay to 11.7 grams? So this is another one where you have to pick the right formula in the very beginning. Since they're talking about half-life, we can't just use our standard AB to the T formula. We have to use AB to the T over K. This is our half-life formula here. Now let's plug in what we can. So we're solving for T on this one because they said how long. So ultimately we need to get T by itself. That means we need to plug in stuff for all of these other letters. So this f of t, that is what we want our sample to turn into. That's our target amount, which is going to be this 11.7 grams we want it to decay to. The a value is what we start with. That's the 40 grams. B, well, since this is half-life, B is going to be 0.5 or 1/2. And then this k value, that's how long you have to wait before the half-life applies. So that's this 9 months. So then we can write 11.7 equals 40 times 0.5 to the t over 9. And at this point, it's time to solve this just like a normal exponential equation. So to start this off, we want to isolate the exponential term. So we'll divide both sides by this 40 to get it out of the way. So that's 11.7 over 40, which I'm not going to bother getting a decimal for yet. I'm just going to, at the very end, figure out what that comes out to. Next, we're going to take the log of both sides. So that's going to be log of 11.7 over 40 equals, now using the pop-out rule, t over 9 log of 0.5. Now I just have to isolate t. So to do that, I multiply by 9 and divide by log of 0.5. So t is going to be 9 times the log of 11.7 over 40, all of that divided by log of 0.5. Let me do that on the calculator now. To do this on the calculator, I'm going to do alpha y equals, and that brings up this little menu with the n over d fraction form. So upstairs I've got log, or rather 9 log of, now I'll do another fraction form here. That's going to be 11.7 divided by 40. And I just like this because I can really see what I'm putting in here without having to worry about did I have enough parentheses. Now down below, we'll arrow down here. We've got the log of 0.5 or 0.5, either way. Close that parentheses just for good measure. And that gives us 15.96. Now that was months because our unit was months up here. So there we go.